exercise, let S be the set consisting of all naturals from 1 to 2026. We denote by PS is power set, that is, the set consisting of all subsets of S. Now, given any two arbitrary subsets A and B of S, whose symmetric difference A delta B is non-empty, we use the symbol XAB to denote the maximum of this symmetric difference. Notice that if A delta B is non-empty, then it is a finite subset of the naturals. As a consequence, it surely admits a maximum. Thus, XAB is well defined. Now, let us impose the following binary relation on PS, where a subset A of S is related to a subset B of S if either A and B are identical, or XAB exists and belongs to B. To understand this definition, let us consider a very simple example where the set A consists of 1, 2, 3, 5, and set B consists of 2, 4, 5, 9. Then their symmetric difference A delta B consists of 1, 3, 4, and 9. Among these four elements, the greatest one is clearly none, which belongs to B. Thus, in this case, we have A precedes B. Now, our mission is to show that this binary relation is indeed a total order on the power set of S, which means we should prove the reflexivity, the antisymmetry, the transitivity, and on top of everything, the totality. Among all these properties, the most challenging one is probably the proof of the transitivity. So here, let us start from the totality, which, as we will see, can simplify slightly our discussion on transitivity later. To this end, let A and B be arbitrary subsets of S. Then either A and B are identical, or they are not. If they are identical, we are done. If they are not, then we know that their symmetric difference A delta B is non-empty. From there, XAB as the maximum of A delta B exists and is unique. Recall that the set difference is the union of two disjoint parts, namely A set minus B and B set minus A. Thus, XAB either belongs to A but not B, in which case B precedes A. Otherwise, XAB belongs to B but not A, in which case A precedes B. In other words, we have shown that either A precedes B, or B precedes A, or A and B are equal to each other, which is the desired trichotomy that justifies the totality. With this totality in hand, to show that this binary relation is a total order, it only remains to show that it is a partial order. The reflexivity is trivial. Actually, for any subset A of S, A is equal to A itself. In particular, based on our definition, this means A precedes or is equal to A, and we're done. The antisymmetry is quite straightforward as well. To see this, let us assume that A and B are arbitrary subsets of S, where A precedes or is equal to B, and B precedes or is equal to A. We want to show that A and B are identical. So let us assume to the contrary that A is not equal to B, in which case we will have the symmetric difference A delta B is non-empty, and hence XAB exists and is unique. Now, for A to precede B, XAB must belong to B set minus A. Similarly, for B to precede A, XAB must belong to A set minus B. Thus, XAB should belong to the intersection of these two, which is empty. As a consequence, we conclude that A and B must be identical. This justifies the antisymmetry. Finally, let us work on the transitivity. Let A, B, C be arbitrary subsets of S, where A precedes or is equal to B, and B precedes or is equal to C. We should show that A precedes or is equal to C. Let us use the proof by contradiction again, by assuming that A does not precede nor is equal to C. Recall, however, that we have already shown this binary relation satisfies the totality. As a consequence, C precedes A strictly. In other words, their symmetric difference A delta C is non-empty. The maximum element XAC belongs to A but not C. Moreover, if C precedes A, then neither A and B can be identical, nor B and C can be identical. Otherwise, it will violate the trichotomy implied by the totality and will lead to a contradiction. So now, let us take a pause and check what we have in our pocket. Right now, we have the following assumptions. That is, A precedes B, B precedes C, and C precedes A. In other words, XAB belongs to B but not A. XBC belongs to C but not B. And XAC belongs to A but not C. Now, we will use all these assumptions to construct a contradiction. More precisely, let us consider the relation between the element XAC and the set B. Either XAC belongs to B or it does not belong to B. And we will show that there will always be a contradiction no matter which case we are in. So first, let us assume that XAC is not an element in B. Since we already know it is an element in A, this means XAC is in A set minus B, which is a subset of A delta B. Thus, XAC must be less than or equal to XAB because XAB is the maximum of A delta B. Furthermore, the equality cannot hold because XAC is not in B while XAB is indeed in B. We claim that XAB does not belong to C. Otherwise, if XAB is in C, then since we already know XAB is not in A, XAB is in C set minus A, which is a subset of A delta C. Thus, XAB must be less than or equal to the maximum of A delta C, which is nobody else but XAC. This is impossible as we have already shown that XAC is strictly less than XAB. Hence, XAB is not in C. But XAB is already in B. This means XAB is in B set minus C, which is a subset of B delta C. From there, we conclude that XAB must be less than or equal to the maximum of B delta C, that is, XBC. Again, the equality here cannot hold because XBC belongs to C, but XAB does not belong to C. Now let us think about the relation between XBC and A. If XBC actually belongs to A, then it belongs to A set minus B, which is a subset of A delta B. From there, XBC should be less than or equal to the maximum of A delta B, which is precisely XAB. In other words, XBC is less than or equal to XAB. This will contradict the inequality we have just achieved. As a result, XBC does not belong to A. From there, since we know XBC is in C, XBC must belong to C set minus A, which is a subset of A delta C. Again, by the definition, we conclude that XBC must be less than or equal to the maximum of this set, that is, XAC. Again, the equality cannot hold, because XBC is not in A, yet XAC is indeed in A. Now we have completed the chain of inequalities. If XAC does not belong to B, then we will have XAC is less than XAB, which is less than XBC, which is in turn less than XAC. Comparing the two ends of this chain, we see we have reached a contradiction. Similarly, if XAC is in B, we will get another chain of inequality which again leads to the same contradiction. We leave the audience to work on the details. Alright, to summarize, if C precedes A, we will always reach a contradiction that is, XAC is less than XAC itself. As a consequence, this assumption is false, and we must have A precedes or is equal to C. This justifies the transitivity. Now that this binary relation indeed satisfies the reflexivity, the antisymmetry, the transitivity, as well as the totality, we conclude that this is indeed a total order on PS.